twin-turbo or biturbo refers to a turbocharged engine in which two turbochargers compress the intake charge. More specifically called parallel twin turbos. Other kinds of turbocharging include sequential turbocharging and staged turbocharging. The latter is used in diesel automobile racing applications. Parallel twin turbo refers to the turbocharger configuration in which two identical turbochargers function simultaneously, splitting the turbocharging duties equally. Each turbocharger is driven by half of the engine's spent exhaust energy. In most applications, the compressed air from both turbos is combined in a common intake manifold and sent to the individual cylinders. Usually, each turbocharger is mounted to its own individual exhaust turbo manifold, but on inline-type engines both turbochargers can be mounted to a single turbo manifold. Parallel twin turbos applied to V-shaped engines are usually mounted with one turbo assigned to each cylinder bank, providing packaging symmetry and simplifying plumbing over a single turbo setup. When used on inline engines, parallel twin turbos are commonly applied with two smaller turbos, which can provide similar performance with less turbo lag than a single larger turbo. Some examples of parallel twin turbo inline engines are Nissan's RB26 DET, BMW's M54 and Volvo's B6284T and B6294T. Some examples of V-formation engines with parallel twin turbos include Mitsubishi's 6A12TT, 6A13TT and 6G72TT, Nissan's VG30 DET and VR38 DET, and Audi's 1997-2002 S4, B5, 1997-2005 A6, and 2003-2017 RS6. While a parallel twin turbo setup theoretically has less turbo lag than a single turbocharger setup, this is not always the case due to many factors. Marginally reduced combined inertial resistance, simplified exhaust plumbing, and the simultaneous spooling of both turbos means that there can still be a noticeable bit of lag, especially in high-flow turbo, high-boost applications. Some ways to counter this are to use a light-pressure setup with smaller turbos, where the turbos are designed to output less boost but spool earlier. While this setup sacrifices some top-end power, it still has less lag than a similar engine with a single turbo setup making the same power. Another system would be the use of variable geometry turbochargers. This system changes the angle of the guide vanes depending on the exhaust pressure, giving the system excellent power throughout the rev range. Once used mainly in turbocharged diesel engines, Chrysler was the first to use it in mass-production gasoline-powered vehicles with the Shelby CSX, debuted in 1989. It is possible to use parallel operation with more than two turbochargers. Two such examples are the Bugatti EB110 and Bugatti Veyron, both of which run four turbochargers in parallel. The EB110 runs four turbos on a 3.5-litre V12 engine, producing 542 horsepower, 404 kilowatts, at 8,000 revolutions per minute, while the Veyron uses an 8.0-litre 16-cylinder engine to generate 1,001 PS, 736 kilowatts, 987 horsepower. The Bugatti Veyron Supersport uses the quad-turbo 8.0 W16 engine that produces 1,216 PS, 894 kilowatts, 1,200 horsepower. Sequential turbos refer to a setup in which the motor uses one turbocharger for lower engine speeds, and a second or both turbochargers at higher engine speeds. Typically, larger high-flow turbochargers are not as efficient at low RPM, resulting in lower intake manifold pressures under these conditions. On the other hand, smaller turbos spool up quickly at low RPM but cannot supply enough air at higher engine speed. During low to mid-engine speeds, when available spent exhaust energy is minimal, only one relatively small turbocharger, called the primary turbocharger, is active. During this period, all of the engine's exhaust energy is directed to the primary turbocharger only, providing the small turbo's benefits of a lower boost threshold, minimal turbo lag, and increased power output at low engine speeds. As RPM increases, the secondary turbocharger is partially activated in order to pre-spool prior to its full utilization. Once a preset engine speed or boost pressure is attained, valves controlling compressor and turbine flow through the secondary turbocharger are opened completely. The primary turbocharger is deactivated at this point in some applications. In this way, a full twin turbocharger setup provides the benefits associated with a larger turbo, including maximum power output, without the disadvantage of increased turbo lag. Sequential turbocharger systems provide a way to decrease turbo lag without compromising ultimate boost output and engine power. Perhaps the most noteworthy application of this system is the fourth-generation Toyota Supra, 1993 to 1998, which is generally regarded as having the most reliable sequential turbo system yet fitted to a production automobile, with a reported failure rate of less than 1% as of 2011. Other examples of cars with a sequential twin-turbo setup include the 1986 to 1988 Porsche 959. The 1990 to 1995 Unos Cosmo JC, 1992 to 2002 Mazda RX-7 Turbo, 13 Biru engine, the 1994 to 2005 JDM Subaru Legacy GT, GTB and before RSK, EJ20 TT engine, and the Peugeot 407 2.2D. GM has filed a patent for a sequential twin-turbo system that uses a new bypass valve design said to optimize exhaust flow to the turbines of both turbochargers. According to the 2016 patent description, the exhaust manifold features two outlets with one directing exhaust gases to the turbine of the high-pressure turbocharger, while the second exhaust manifold outlet directs exhaust gases to the turbine of the low-pressure turbocharger via a connecting channel. Additionally, exhaust gas exiting the high-pressure turbine is directed to the inlet of the low-pressure turbine. The new bypass system features two throttle valves located on the same spindle mounted perpendicular to each other. With the throttle valves mounted on the same plane, one valve opens to direct exhaust gas flow to one of the turbochargers while the other valves simultaneously blocks exhaust gas flow to the other turbocharger. The vehicle ECU, electronic control unit, sends a signal to the spindle's actuator to rotate the throttle valves based on RPM and load. GM says the new design allows engineers to optimize exhaust gas flow to both turbines without the compromises of traditional sequential turbocharger systems. Additionally, the system could utilize a variable geometry turbine or a fixed geometry turbine on the high-pressure turbo.